So, how to design and build AI applications with vector search using Azure OpenAI and Azure Cosmos DB. There's a long title. So I have to admit, this was a pretty hard session to prepare for, not because I don't have enough content, but because there are about 1 billion YouTube videos and podcasts and articles all over the place, everywhere at the moment. So I've absolutely no idea how much you already know. Please forgive me if I'm telling you things you already know. But I can guarantee that nobody will present it exactly the same way as me, so at least there is that. So a little bit about me. My name's Theo. I'm a program manager in the Cosmos DB engineering team. I lead what we call the Java developer ecosystem for Cosmos DB, as well as high availability, and our Apache Cassandra offerings. You'll notice I don't work in the AI department. I don't work on vector search within the team, so I've been coached a little by my colleagues for the session today. Having said that, I did do a master's degree, believe it or not, in data science many moons ago. I used Markov chains to model clickstream data and created a new consensus clustering algorithm. I was very proud of myself at the time. But these days, every couple of months, I get emails from PhD students asking me how the code works, to which I reply, I haven't got the faintest idea because I haven't looked at the code for 7 years. But anyway, yeah, I had some involvement in that space, and now I'm having some involvement again. So, a little bit of an agenda then. We're going to have some fun with what is AI? What is the definition of artificial intelligence? Is anybody really asking that question anymore? I thought I needed to fill some space, so I added this in and then realized I had too much content, but it's in there now, so I'm going to go with it. We'll talk about some challenges into the more meaty stuff for AI apps today. Some important concepts for building AI apps. I'm going to talk about Azure Cosmos DB Mongo vCore API, and also the roadmap for Cosmos DB as a wider platform for AI, and then a little bit on Query Copilot for Cosmos DB at the end. So, what is artificial intelligence? If you were to put in Google, what is artificial intelligence? Microsoft blog, the second entry that you'd see was an article published in 2018 on Microsoft blog written by me. And at that time, the reason I wrote the article, well, one was to introduce people who were new to AI at the time, give them a soft introduction, give them a little code sample of building a primitive AI app. But the real reason was that I was frustrated with the definition of the term. Artificial intelligence, to me, is a little bit like the word God or genius or these other words that we use, which we kind of know the meaning of, but everybody has a completely different idea in their mind about what it actually means. At one end of the spectrum, you have people who just think AI, or at least the state of AI as it is today, is just more complex code than we had yesterday. After all, computers are machines, and they do things that would otherwise be done by human beings, and so, isn't that all AI is? I have to admit, I kind of fall into that bucket. But then at the other end of the spectrum, you've got people who are thinking about conscious machines and scary Skynet Terminators and Armageddon and so on. And that's what really AI is. And until we're there, then we shouldn't be talking about it. Or maybe we already are there. Maybe LLMs are the advent of general intelligence and crying computers and so on. At this point, I'm going to quote an old friend. Has anybody heard of Tim Scarf here? Anybody met him? No, he's the founder of a podcast and a YouTube channel. I think it's the most subscribed YouTube channel for machine learning at the moment. I can highly recommend it if you've never watched it. It's insanely deep, unbelievably technical, and so it's really staggering that it gets as many subscribers and views as it does, because you get into about an hour of the content and the average person will be completely lost. Tim's a very smart guy, and he said this, which I think is really brilliant. He said, "It's a common misconception thinking that LLMs are creative. LLMs perform diffused retrieval given a prompt. They are basically databases." How many of you are database fans here? How many of you are database people? Isn't that music to your ears? LLMs are basically databases. Indeed, a new form of database. This is really, really brilliant insight. An agent conceiving a prompt in the first place might have been creative if its action was surprising given its situation. Only agents with sufficient functional dynamics to plan can be creative by definition. LLMs have no functional dynamics, no agency, therefore LLMs are not creative. Ouch. Wow. I did say it would be controversial. These aren't my words. These are not my thoughts. But Tim Scarf is a leading voice out there in the machine learning world, and he's saying this. So, okay, maybe we can agree LLMs are not Skynet, but surely they have moved on, right? Things have moved on in the field of AI. Certainly when I wrote that article, if you were to read it now, you would think, wow, that is so primitive. We can easily do all of this stuff with ChatGPT. We've all seen it. We've all typed things in. We've all seen how powerful this is. And Tim goes on to say, another interesting feature of LLMs is their surprising degree of factfulness at large scale and responding as if they understand the prompt and as if they were reasoning, which of course they are not in the way that humans do mostly. This is because factful things are statistically more likely given internet data and common prompts, and even more so how OpenAI have curated the training data. Autoregressive pattern matching is a crude form of reasoning. The clever thing is that a lot of what we think is reasoning can be formulated as diffused information retrieval. It's a database. Even more so, given the generative inductive priors and the uncanny valley effect and anthropomorphism, some big words from Tim there, fooling us into thinking LLMs are doing more than they actually do. So I think you probably will get the impression now that Tim's quite a controversial, or let's say a skeptical person in the machine learning world. He certainly falls on the same side of the camp that I do, of thinking, yeah, this is just more complex algorithms than we had yesterday. But this is quite charitable by his standards. He's obviously recognizing that there's been a step change here in what we can do. I couldn't have imagined this 5 years ago. I still think machine learning and essentially AI has the same restrictions as it always did, but this is quite a big jump. And then it goes on to say, the autonomy gap is where the magic fades. It quickly becomes obvious LLMs have zero intelligence. Yeah, you can take a picture. There is no intelligence without autonomy. LLMs have no autonomy. Therefore, LLMs are not intelligent. When you turn an LLM into an agent, it diverges and decoheres exponentially fast. The only way you can prevent this mode collapse is by setting extremely tight operating constraints with careful prompting, etc. So the reason I'm laboring this point and talking about how we should sort of circumscribe the way we think about this is, of course, you've come here to learn about how to build and design AI systems or systems with more complex code than we had yesterday. And the way to do that is to follow the general best practices that are out there. Personally, I would rather think of this as a new paradigm in developing applications. We can call it AI, that's fine. I'll continue calling it AI. Stay on message, Theo. The reason I'm saying all of this is, well, one of the reasons is, if you, like I said already, I already alluded to it, as far as I can tell, and I admit I've not done the academic research into large language models or even their progenitors, neural networks and transformers and so on, so I haven't gone deep into that, but as far as I can tell from the literature, LLMs have the same constraints as any machine learning modeling architecture in that they need to be trained on data, they need to avoid statistical overfitting and underfitting in order to generalize to a population, and that means a margin for error. And when you have a margin for error, then things can go wrong, obviously. And the difference between LLMs and more primitive models, let's say, like let's take, for example, logistic regression. You're predicting a very discrete thing. Predict if a crack is greater than 10 millimeters, a crack greater than 10 millimeters will occur in a manufacturing process, say. It's very discrete. But an LLM is predicting what the next word should be in a response, which is spectacularly sophisticated and complicated, right? And don't get me wrong, I'm very impressed. But we've all seen what happens when the predictions start to go wrong, right? There's so-called hallucinations. It all goes completely wrong. The point I'm making here is they're not understanding. They're not perceiving. They're not creative. You still have to give them instructions. In a sense, I agree with what Tim says. They are effectively, I won't say glorified databases, but a new paradigm shift in databases. You could say that. You could say they're like databases, and they have a new query language, albeit a very human-like query language, but it still needs to be engineered, and there still needs to be operational constraints and so on. So, a bit more into the meat of things. Challenges for AI apps. Modern intelligent applications of any sort, regardless of whether they're AI or not, have unique requirements today. Everybody sees this and knows this. Data is highly available and unstructured, variable, high-volume traffic, fast, real-time. They need to be always on, 24/7 digital experiences, and globally distributed. Of course, for Cosmos DB famously was the first globally distributed database service. And of course, as everybody knows by now, everyone's talking about AI. What can you do with it? Well, there's plenty of use cases, obviously. Connected smart products, transaction processing at scale, real-time fraud detection, service and bot support, information and product discovery, personalized recommender systems, and building your own co-pilots. And there's many more, I'm sure, that will emerge. AI-ready databases, as far as we, Microsoft, are concerned, will allow you to store your data and your vectors together. There are reasons for that hopefully will become clear. They're best for semi-structured and dynamic data. So yes, NoSQL databases are more conducive to this. They handle semi-structured data better. High scale, instant auto scale, preferably low latency, real-time data transactions, mission critical, reliability, high uptime, and native vector search, which I'll get onto. So, we're done with the challenges. So, some important concepts for building AI apps. We'll talk about generative AI scenarios, vector embeddings and vector search, and the vector indexes that we support today and will support in the near future. So, generally speaking, the four sort of themes or things that come out of the use cases that we see people using Cosmos DB and the offerings that Cosmos DB has in the AI space. Vector databases, of course. People don't just want to store vectors in memory because it doesn't scale, and they also want to be able to store chat history and chat memory and use semantic caching together, and for that you need a database. Retrieval augmented generation, or so-called the RAG pattern, which I'll talk about if you haven't heard about it. This is where you are using your own data to augment the information that the language model would otherwise be retrieving from its own vast training data set in order to remove the margin for error, as it were, the inaccuracy. Chat history. This is actually a really big use case, and we've seen this for quite some time, since well before LLMs came to the fore. Databases, systems are storing their data, their chat history in Cosmos DB. It's quite clear why this is, not only because they want to analyze user trends, but also improve the models, improve the performance, use them for fine-tuning. And in this case, I don't really mean retraining the model. This is one thing that has changed, definitely changed in a big way from when I was thinking about this 5-6 years ago. The models are such, or this type of modeling architecture is such that you're not retraining it, you're just retuning it, reprogramming it, prompting the model. The model itself, the training data set, and the depth of what it can do with language transformation is, generally speaking, enough. You just need to augment it with new data and with new prompts, and also have a decent vector search approach, and with trade-offs between accuracy and performance, which we'll touch on a little bit later. So what vector indexes are supported in Cosmos DB and Azure Database for PostSQL, which is an API served by Cosmos DB. Inverted file index. So this is the least scalable and most primitive, partitions vectors into clusters and assigns each vector to one cluster. The more clusters you have, the more predictive the result is, but potentially the less accurate, but the more performant it is. And you see the same thing through all of these indexes. HNSW, hierarchical navigable small world, slightly more scalable still, but then requiring more resource. Disk ANN is the most scalable, can handle very large data sets. Now, I mentioned disk ANN The only product, as of today, in Cosmos DB, the only offering under Cosmos DB that supports this is a product called Azure Managed Instance for Cassandra, which I work on. So if you want to talk about Cassandra, if you have customers using Cassandra, or you're a customer that's using Cassandra, this is a great service, even though I do say so myself. You can think of it like the AKS for Cassandra. It's just a service for open source Cassandra, and we're pushing that out there and making it the easiest place to run Cassandra in Azure. I won't say anything more about it because I'll be going far too far off track, but just wanted to mention it, and it uses disk-ANN, or an implementation, the open source Java implementation of disk-ANN at least. The NoSQL API, the mothership in Cosmos DB, will be getting vector indexing soon. We'll be announcing that in build 2024. So onto some concepts that I mentioned earlier. Vector embeddings, for those of you who don't know, what this means is you're compacting your data into semantically rich representations of the data in numerical form, basically arrays of floating point numbers. The vectors, when searching for them, are considered semantically close if they are a close mathematical distance expressed as cosine, similarity, dot product, Euclidean, and so on. This has been around for years, by the way. Vector search concepts are not new. What's new is the idea of needing them to be scalable and embedded into the database, which is what we've been working on frantically for the past several months or so, and will be doing into the future. And it's easy to generate embeddings these days. There's plenty of APIs out there, not just OpenAI. Mentioned the use cases before, but here are some of them again, answering questions, detecting anomalies, and so on. Retrieval augmented generation. So this is where you will inject data into the process. Remember, I said this is why I labored the point earlier on about LLMs not, although being very impressive in the way that they can generate responses, there's no understanding there. So it's very easy for them to, I won't say it's easy for them to go wrong, but when they go wrong, they really go wrong, right? So that's where you need to inject accuracy into the process, to give them a circumspect space to work on. They're not autonomous in any way. So if you give them a circumspect space to work on and then coach them using prompting with the data that you've retrieved, using a vector search that's based on some similarity to the question that's coming in, then you get a much more predictable response. That's what you want, is some kind of predictability, albeit this is all based on statistics and probability, so you're not always going to get the same question and answer, but that's what you're driving towards. So why should I care about chat history? I mentioned that just before. Of course, memory. Short-term, long-term memory of your LLM conversations brings a richer semantic context. The more chat history that you bring in, the better the response will be in the completion API of whatever LLM that you're using. User analysis, it makes the model better if you can analyze what people are saying in response, how they're feeding back. You can use that to inject prompts automatically and make your model better. It's not actually making the model better, it's making the model's response to questions better. Semantic caching is one related technique that you can use here. It's a trade-off between performance and the accuracy of the response. I'll show a demo of it if I get time at the end, but basically you ask a question or you receive an input. The model will give you a response, but that will take a certain amount of time because it has to search its the internal model for an answer, and that can take quite some time. But if you've already cached that response, and all you're doing is a similarity search on the question to get the answer that was given to a similar question, then you can give that question back, and obviously that will be much quicker. Obviously, there's a degradation of accuracy there, because if you just give the response to a similar question instead of giving the response that the model would give to the question, then obviously your response may degrade, but that may be sufficient for the trade-off that you're looking for in terms of performance and accuracy. The classic trade-off in databases is performance or latency and availability versus consistency. If you think about the CAP theorem, we're just adding another trade-off in this development space of accuracy as well. But yeah, it's just another database, isn't it? So there's just another trade-off. Customers have used, I mentioned this before, customers have used Cosmos DB for chat for years, including some big Teams, little joke there, Teams uses Cosmos DB. Practically every service that's online in Microsoft uses Cosmos DB by now. Not least of all, OpenAI. OpenAI is built on Cosmos DB, so your AI-powered apps can be too. There's no reason why not. Incidentally, OpenAI uses Java and Python. Mostly Python, there's quite some Java as well. If that means anything to you, I'm sure they use other languages, but those are the main ones that they use. Right, so on to Mongo vCore. Cosmos DB is a family of scalable, highly scalable distributed database products. As of today, the API that has a GA version of vector search is Mongo vCore. To anticipate the question that you may ask, the reason that we haven't implemented this yet in NoSQL is because it was easier to implement it in vCore first. The architecture was more conducive to it. It will come in NoSQL API. Don't worry about that. Certainly, OpenAI will want to use it. They're practically our biggest customer at the moment. But they can both be used to build AI applications. It's not just about vector search. It's about a whole lot of other things as well, obviously. So vector search, like I already mentioned, there's another trade-off in addition to the trade-offs that you already have to manage in a database between performance and consistency, and that is of accuracy. And here you'll see, again, just like with scalability, also with accuracy, the HNSW and DiskANN recall, the accuracy remains stable even at high throughput, especially DiskANN. NoSQL will be, vector search will be developed using DiskANN. A new implementation, an improved implementation of DiskANN. I don't think I can say any more about it, otherwise I'll be told off by someone, but I'll say no more than that for now. Okay. There's a few slides here I'm going to skip past because it's just talking about Mongo vCore, and it's a bit salesy, but it's a GA offering. The growth on it has been pretty unexpectedly high. Lots of customers are using it, mostly for building AI apps, no surprise there. And some new additions recently, we've added a free tier, so if you need to try it out, there's no cost. Burstable SKUs, new cluster tiers and storage, private link, migration tools if you're migrating from native MongoDB, native vector search. It includes HNSW now, will include DiskANN in the future, I think. Let me think about that. Maybe not, actually. I'm not sure about that. Certainly, HNSW will go into GA fairly soon. Integrations with the various abstractions, which I'll talk a little bit more about later, LangChain, semantic kernel. If you're familiar with things like Spring Data or Entity Framework, whatever, abstractions over the native APIs, it's that kind of thing. But for LLMs and embedding stores, they have their pros and cons. I'll talk about it a bit later on. And integration with Azure OpenAI Studio. And don't forget to grab that link at the bottom, try vCore. It's very easy to try out if you're building an AI app. There's a few use cases that have been really great for those customers that they allowed us to share. KPMG for their operational tasks, improving productivity, which after all is what the game is all about in technology, reducing overheads and so on. And TomTom, anybody have TomTom SatNav, or is it, or are you all using your Apple iPhones now? First, yeah, you used to use it. Yeah. Okay, well, it's still used somewhere, and they use Azure OpenAI, Cosmos DB, AKS, and that's their architecture. So yeah, vCore integrations, the abstraction framework, semantic kernel, llama index, LangChain, and Azure OpenAI vector database. And so I'm going to skip over this basic AI app architecture, so I've got a diagram in a couple of slides that's a bit easier to follow, but we'll get into some demos. So first of all, using your own data with Cosmos DB for vCore and Azure OpenAI in a simple app, a very contrived app for the purposes of showing just the main building blocks of what you'd be doing. There's a link there to a demo sample. It's very easy to use. It's in Java. Apologies if you don't know Java. It's just my wheelhouse, so I had to write this in Java. So a little much simplified diagram, the anatomy of a generative AI app built using the RAG pattern retrieval augmented generation. Typically, to begin with, at some point you will load documents, data from some documents, could be PDFs, text files. You'll be vectorizing those using OpenAI and storing them in a vector store. You'll then use OpenAI to vectorize the questions or inputs that will be coming into your system and then search against the vector store for the most relevant data to that question or the most semantically similar data to that question. You will then use, or the system will then use, the contextual data that you get back from the vector store along with the chat history and along with your prompt in order to formulate a good response. If you're smart, you'll also store the chat history for later so that you can improve the process as things go along and also analyze user trends as well. And then finally, the system will complete and formulate a good response calling the chat completion API. And it's pretty much the same in all of these LLM models, but I don't want to give too much airplay to them. We're just talking about OpenAI and Cosmos DB. So, a demo of this in action. Again, apologies, it's Java. If you've never seen Java before, look away. Or if well, all programming languages are the same, aren't they? So anyway, so loading data into. So here it's a simple Spring Data app. Even if you've never touched Java before, I'm sure you'd be able to run this. So just going to load 3 very simple files into the system. Cosmos DB is the best database in the world. Another file saying Liverpool is the best football team. Another file saying how to unify quantum physics and general relativity. The answer is 42. Those are the files we've loaded in. Let's look at our vector store. And yeah, here we are. There's that text. So we've got 3 vectors, and we can see that they've been embedded, and we can see the numerical representations, the arrays of floating point numbers is how we've represented the data. So that's what we have. That's our very simple, very contrived vector store. And now the app is going to use OpenAI to vectorize a question that comes in. So let's start up our app. It'll take a little bit of time to fire up. And yeah, so we go to, this actually just a ChatGPT-like experience. I'm just going to put a question in, tell me about the theory of everything. And hit send, and it's going to go straight into debug. The question is coming in. We're going to call the get embeddings API in order to vectorize that question. And you can probably guess what you were going to see next. Underneath the response, we can see the data that question has been numerically represented or embedded in vector format, and then we are going to call the search, a vector search command in the database, which is going to bring back some results. Now, I've capped it at 5 results, but of course, we only have 3 documents in the vector store, so it's going to bring back all 3 documents. This is where you might want to limit the number of results that come back if it means that some results that come back are not going to be relevant. But at least we'll always, in this case, rank the most relevant result. I want to point out that all of those results will be used as part of the feeding into the chat completion API. You don't have to use them all, but that's typically the approach. In this case, we'll just have 3 entries, 2 of which are not relevant. So third step, use the contextual data and chat history to populate a GPT prompt. So not surprising, we're going to populate this. And here is the prompt. Pretty basic. Context information is below. Given the information and not prior knowledge, answer the question. Very basic prompt. But isn't it fantastic? You can just use English to program now. Just speak English to the model and just tell it what to do. And that's the really impressive thing for me, is that you can just, we're beyond high-level programming language semantics now. We're getting into just human language. And so there we go. And of course, we're going to store the chat history for posterity and for use later on. Of course, this app is very contrived, so I'm not going to do anything with it. But little tip, if you're going to build AI apps, think about storing the chat history. Think about what you're going to do with it. Think about building workflows to create pipelines that are going to evaluate the success and maybe change prompting. You can work out ways of automating how you change prompting as well. Haven't shown any of that here. And then finally, the app will use OpenAI chat completion to formulate a good response. I wonder if this will be a good response. Anybody think it will give, what do you think is going to happen here? Based on the context information provided, there is no clear or direct information about the theory of everything. The first sentence about unifying quantum physics and general relativity is a reference to a popular science fiction book, Hitchcock. Slightly embarrassing. I wouldn't like to see that happen in my app. So yeah, I need better prompt engineering. So yeah, instead of just saying answer the question, if you can't answer the question, do not answer it. What do I get this time? Okay, a little bit better. There's no direct answer to the question, but it's still kind of embellishing and adding too much information. No, I need to be a bit more specific. Just say you cannot answer it and don't add information. And what do we get this time? Okay, so that's better. But suppose I try and be a bit too clever. Suppose I say, well, it couldn't answer the question from the context information. Didn't think that even though that was the most relevant data that I had in my data store, it was relevant to the question. Suppose I try and be too clever and say, if you can't answer the question, use the most relevant contextual information as the answer, and do not add more information. Will it give me the right answer? Well, yes, or the answer that I wanted. But what's it going to do now when I ask a different question that's similar? Similarity. It's going to give me the same answer, right? So obviously it's a trial and error. You've got to be careful. You have to experiment. And I will warn you, LLMs are obviously not deterministic. So you have to put, like Tim Scarf said, tight operational controls on the data that you provide it with and the prompts. If you give it really good prompts, and you're very circumspect around this, and you do lots of testing around it, and you build in processes that are going to learn from whether it makes mistakes, you can build really good, intelligent, great AI systems. This is another demo. How much time have we got left? 16 minutes, right. I probably haven't got, this is basically doing the same thing, right? So, but it's a more complex, again, this is a sample that you can look at. It's got more composite parts and different languages and so on. This piece is in Java, obviously. I'm doing exactly the same thing, but just a little bit more data in the vector store. It's a product, what was it? It's a fitness app, and then so there's some product information there. And then there's a fitness assistant incorporated into the app. And so, yeah, you can see a lot more in there. So I'm going to skip past this, otherwise I'm not going to get through everything. I will show this because it's a world exclusive. We have just, maybe not the most exciting world exclusive, but we just recently pushed out changes in the Java LangChain framework to support Cosmos DB Mongo vCore. That link, as of right now, links to one of our developers' GitHub account dev branches with the sample. Eventually, it will be updated with the full public sample, but if you're really curious, go and have a look. The idea behind LangChain, this is a very contrived sample, obviously the idea behind LangChain and the other similar frameworks is, as I said, to abstract away the native API specifics of hand cranking, what you need to do for specifically OpenAI, specifically Cosmos DB, and other vector stores, and other LLM models. One thing that I haven't mentioned, I think, in the other demos, if you're building an app like this, you're going to be providing credentials for OpenAI, an endpoint and an API key. You're going to be providing a chat model, a chat completion model, and there's different types of models that have different types of performance and different characteristics, and you're going to be providing an embeddings model, again, different types of embeddings or different depth, different level of dimensionality. Again, there's trade-offs between accuracy and performance there as well. There's multiple different dials in this space, and then you're going to be providing a vector store. And so in LangChain has lots of features, but it abstracts the differences between different vector stores and different LLM models. So this will implement a chat language model, which exposes a number of interface methods that we have to comply with in our contract. So all of the code basically will look the same, regardless of what LLM model you're using or what vector store you're using. So in the end, it should be able to do the same thing, but it's just a lot less boilerplate. So let's have a look at what happens here. This is a bit more of a, if you're brand new to this and you haven't tried doing this before, maybe using something like LangChain or a sample like this is the best thing to start with, because it abstracts away all the boilerplate. You can just see what's happening. You can see the components that you need to have in order to build this, and it's all just very sort of simple. I'm going to type in the same thing. What answer will it give me? I can't remember. What is the answer to the theory of everything? Does it give me the same answer? Yeah, obviously I trained it well this time. So how much time have we got left? Am I okay? 13 minutes. Wow. Okay. And we also have in preview Copilot for Cosmos DB. So this is, as the name implies, it's a Copilot for Cosmos DB, natural language. Type in what you want to see from the database, and it will convert that sentence into a query. And to be honest, maybe I don't need to skip through things this quickly, but if you have a Cosmos DB account, you can pretty much try this out. It's very straightforward. You just put in something like show me the first 5 items, or something more complicated. But again, as long as it's well described, it will convert the query well. If there's any ambiguity, it might not do. But we really want to see the feedback. So if you wouldn't mind, if you're interested in Cosmos DB or using Cosmos DB already and you haven't tried this out, please do try it out. And please click the feedback thing, which is somewhere. Where is it? I think I show it. Oh, I think James shows it at the end. I didn't do this demo, so let's see what happens. Show me movies that James Bond in the overview were produced in France along with the year they were released. That's pretty good. It's giving you 2 things. It will give you the original prompt and then an explanation of the query and then the query itself. Then you execute the query. And then, if you would, put the link, tick the thumbs up or thumbs down, and then click on the link. And if you wouldn't mind giving us feedback, that would be awesome, because that helps us to improve the process in the same way as you will be doing when you're building your AI apps. And I'm sure I had another demo. I did have another demo to show. There's one more thing. I did want to just show, this is a live demo, so it may go wrong. So this is, I probably haven't got time to walk through everything that's happening here, but this is a sample. Again, there's links to all of this in the deck for semantic caching. So in fact, let me just run this through. I'll just point out the one thing that's important here. There's a bit here, namespace, and it's just identifying a caching collection. That's what's going to store in a vector store with an index the question and the answer, and then every subsequent question that comes in, it's going to search that store. If it finds an answer, it will give, if it finds a semantically similar question, it will give the answer that was given originally to that question. The idea behind this is trade-off between performance and accuracy. So, oh, it's still running. Internet must be a bit slower here than in my bedroom. Is it actually running? Oh, it's run.
Can I ask?
Yeah, please.
So the caching layer, is it being built on the Azure Cosmos DB or
Yeah.
do you have it as part of your code logic?
No, it's. I'll repeat the question. Is the caching layer being built on Cosmos DB, or is it part of some caching in-memory layer? No, it's in Cosmos DB. So when we say cache, what we really mean is a layer that is going to respond faster than the normal way of service, right? So you can see here, which is what I was about to show, the first question, tell me something about beer making, took, it's up here, yeah, tell me something about beer making took nearly 7 seconds to come back from the LLM model. The next time that question was asked, it took 580 milliseconds because it was coming from the cache, Cosmos DB, with a semantic search. Then another question was asked, how do I make beer? That's not quite the same, is it? But it's very similar, so the same answer was given. You see the kind of trade-off between accuracy and performance. It's quick, but if you fed that into the LLM model, you would have got a slightly different answer, I think. Maybe a more direct answer. But is this answer good enough? Maybe so. This is the kind of trade-off that you need to weigh up.
And does the cache store both the question and answer?
Yeah.
And then based on that?
Yeah, and LangChain, sorry, I'll repeat the question. Does the cache store both the question and answer? Yes, it does. Yeah. And LangChain will abstract away the complexities of doing that for you, amongst other things that it will do. You can hand crank all of these things, but it's like the difference between any low-level SDK or client driver versus using some framework that does all the boilerplate for you. And then, yeah, last thing that I wanted to mention, if you've not already seen it, we have an Azure AI Advantage free offer, up to £6,000 worth of Azure Cosmos DB for 90 days if you're using AI services. Personally, if I was you, I would wait maybe a month or two until the announcement of vector search in NoSQL API, because then you'll be able to take advantage of this and use the preview of vector search when that comes out. Believe this only applies to NoSQL API. It doesn't apply to MongoDB Core, unfortunately. But yes, it certainly will still apply when vector search is there as a capability as well. And there's plenty of resources on Microsoft Learn about all of this stuff. If you want to take a photo, please take it now. Those are all of the resources that I used in the presentation. Links to samples and documentation. And I think we're showing the slides anyway, so. And then there's a bunch more resources as well. A few of the things I showed there, most of it I didn't. So there's a ton of information for you there. Thanks very much. And lastly, if you enjoyed the session, please snap the QR code. If you didn't enjoy the session, there is no QR code. These are not the droids you're looking for. All right, so have we got, how much time have we got left? Time for questions?
6 minutes.
Great. I'm happy to answer questions, especially about Java, SDK, Cosmos DB, high availability, and Cassandra, but you can feel free to fire any questions. Yeah, so how do you know, the question is, when you're loading in data into a vector store, how do you tell the system, as it were, to prioritize between that and the corpus of data in the LLM model, right? So this is really, it's a good question. By default, if you are using vector search, you're prioritizing your own data. The extent to which it will be prioritized will be governed by the quality of your prompting and the accuracy of the search as well. So it's a combination of those two. And the tuning parameters as well. I didn't mention them in the presentation, but there are things like temperature, which is the amount of randomness that the response will include. I think it's from 0 to 2. 0.1 would be very deterministic, for example. There are other parameters as well. I didn't mention them all, but they're not difficult to pick up. So it's a combination of those things as to how much it will use its own sort of internal training data. So if, for example, if you come back with an answer from the vector store that just isn't relevant, it will use its own data. That's because you haven't done a good enough job with vector search and with procuring enough data, just as an example. So that's how it's governed. Yeah. Good question. Any more questions? Speak now. Yeah. Yeah. So I'll repeat the question. So you've heard from people that running machine learning workloads costs a lot in terms of GPUs and cores and things like that. So in this case, I don't know sorry if it wasn't clear, but OpenAI is a cloud service. You're not paying for the training of the model. That's the expensive thing in the context that you're talking about in terms of GPUs and resources and so on. Calling the APIs, you're just calling an API that's exposing a model that's already been trained. And the cost of that is fairly, well, I think it's reasonable. I don't know what you'll think when you look at the pricing. I'm certainly not an expert on the pricing for OpenAI, but it's certainly nowhere near the kind of cost. I know what you're talking about if you're running these models yourself, but see, we've already stepped beyond that now. We don't need to do that anymore. Users of these models don't need to do that anymore. It's been democratized in that sense. And what's really amazing, the big impressive thing about LLMs is that for this space, the space of language and answering and responding to questions, you don't really need to train the models anymore. That work has been done. Now it's all about augmenting the accuracy of the responses and balancing the trade-offs with performance. So it's actually quite cost-effective, which explains why so many people are doing it. Sure, yeah. Why it is that way? The question is what's a good example of a solution that uses all of the parameters and the aspects, and why was that a good solution? That's a good question. I think, obviously I'm going to say OpenAI is a good solution, but that's kind of not really the question. That's now become the service that people consume. The KPMG solution looks pretty good to me. It uses all of the components, and it massively ramped up productivity, and the accuracy of the model was good, and the performance was reasonable as well for their uses. So that was a good solution. The TomTom solution as well, we show those because those were good solutions that the customer was happy with as well. And I like the TomTom one because if I'm not mistaken, it uses voice recognition as well. So there's the whole end-to-end experience, and then it's using the model to sort of guide the user and be very interactive. And so again, they have used everything that I've just described there. Obviously, I'm going to say a solution that uses everything that I've just described is going to be a good solution. Maybe I'm a little bit biased. There are certainly other techniques that can be used, and they're emerging all the time. I must admit, don't think of me as the authority here, and it's a nascent space. It's growing all the time. But those two were good solutions. I know that for certain, yeah. The question was, you can talk about OpenAI. Can you talk about OpenAI? Yes. We're at time, but I'll answer that last question since it was such a nice question. In the beginning, it wasn't very good. It was, as you might have remembered, it was crashing a lot. When people were using ChatGPT, it wasn't scalable. What did they do to solve that problem? You probably guess what the answer is. They started using a scalable database that's conducive to storing the type of data that they need to store in their application. Now they rely completely on Cosmos DB. If you're building a scalable AI system that's going to be consumed by a lot of people, there are a lot of performance trade-offs that you need to take into account. You want a scalable, highly available database to do that. So yeah, OpenAI are a very good customer. That's for sure. Yeah. All right. Are we cut? Yeah. Is that a wrap? Yeah. Thanks. Thanks very much.